Welcome to the Explainer. Today we're going to pull back the curtain on the engineering of our power grid. We're going to hunt down an invisible energy thief that's running 24/7 and then explore the really clever but, well, let's just say imperfect solutions engineers have come up with to try and stop it.
So, let's start with a question. What if there was this massive leak in our energy system? One that's always on, just constantly wasting an incredible amount of power before you even get a chance to use it. Well, there is, and the way engineers have tried to fix it is a fascinating story about compromise.
All right, so what is this problem exactly? Well, it's a type of energy loss that's happening all the time, completely in the background, long before you even think about flipping a switch. You know, we usually think about electricity when we're actually using it, plugging in our laptop, turning on the TV, but the truth is a huge chunk of the power generated at the plant never even makes it to the outlet. It just vanishes along the way. And this gets to the heart of it. It's called no-load loss. A really good way to think about this is to imagine a car, just sitting in the driveway idling forever. It's constantly burning gas, but it's not going anywhere. That's pretty much exactly what's happening with some key parts of our power grid.
And the main culprit here is the humble transformer. You've seen these metal boxes everywhere. They are the absolute backbone of the grid, stepping voltage up and down so we can use it safely. But here's the thing, they are always on, always connected, and always sipping a little bit of power. Now multiply that tiny sip by millions and millions of transformers, and suddenly that little bit becomes a massive, invisible drain.
So how in the world do you fix a device that wastes energy just by existing? Well, engineers came up with a pretty brilliant solution. They didn't really change the design, they changed the very material it's made out of.
And this is it. It's called an amorphous transformer. Now, that name sounds super complicated, I know, but the secret to it is actually really simple. It all comes down to how the atoms are arranged in the metal core.
Okay, check this out, because this is the key difference. A normal transformer core uses silicon steel, where all the atoms are locked into this perfectly neat, orderly grid, kind of like a brick wall. But the amorphous core, its atoms are just randomly jumbled up, with no pattern at all. Think of it like a messy structure that has less internal friction. It makes it way easier for the magnetic field to do its job, which in turn wastes a whole lot less energy.
And the result of that one simple change at the atomic level is, well, it's staggering. Amorphous transformers can slash the main type of no-load loss, which is called iron loss, by up to 75%. That is a huge energy saving, all from just scrambling the atoms in the metal.
But, as you've probably guessed, and as it is with pretty much any big leap forward in engineering, this incredible efficiency doesn't come for free. It actually creates a whole new set of problems you have to solve.
So, the big advantage is a game changer. I mean, we are talking about a massive, continuous cut in wasted energy across the entire grid. That saves money, it reduces emissions, it just makes the whole system more sustainable. Okay, and it's a big but. That amazing benefit comes with some serious downsides. First, that same amorphous metal that makes it so efficient is also really hard and brittle, which makes them expensive and tricky to manufacture. They also tend to be noisier, you can't build them in really large sizes, and because they cost so much up front, it can take a really long time for the energy savings to actually pay for the initial investment.
And this right here, this is engineering in a nutshell. There's almost never a perfect, one-size-fits-all solution. Every choice you make, even a really smart one, is a trade-off between performance, cost, and just practicality.
And this whole theme of solving one problem only to create another, it just keeps going. Let's look somewhere else on the grid, at power capacitors. They're super important for efficiency, but guess what? They bring their own completely different challenge to the table: huge electrical surges.
So, these power capacitors are vital for keeping the grid's voltage nice and stable. But when you switch one on, it acts like a bone-dry sponge hitting water. It just tries to soak up a massive amount of electricity all at once. This creates what's called an inrush current, and this surge can be so powerful it can literally damage other equipment on the grid. So, you've got this component creating these dangerous electrical spikes. How do you tame it? Well, the engineering answer is to add yet another specialized device into the circuit just to control it. And that device is called a series reactor. You can basically think of it as a bouncer, or maybe a shock absorber, for the power capacitor. Its whole job is to stand in front of that capacitor and manage the flow of electricity to stop those damaging surges before they happen. And what it does is pretty incredible. The series reactor smooths out that wild inrush current, it stops other voltage spikes, And it even cleans up the electrical signal by getting rid of unwanted noise, called harmonic distortion. Basically, it tames the capacitor and makes the whole system safer and much more reliable.
But I think by now you've probably spotted the pattern, right? This really elegant solution to the search problem, it introduces its own, you guessed it, inevitable trade-off.
Because the series reactor is holding back and controlling the flow of electricity, it actually makes the voltage and current on the capacitor itself go up, in this particular case, by about 6.38%.
And there it is, the trade-off. While the reactor is protecting the rest of the grid from those dangerous surges, it's putting the capacitor itself under more electrical stress. And all that extra stress? It generates more heat, which can affect all the equipment around it.
And this is really the hidden story of the modern world we've built. Every single step we take to make things more efficient is this delicate, constant balancing act. You solve one problem over here and you create a new one over there. You improve performance, but you increase the cost or the stress on the system. There's just no single perfect fix.
Which really leaves us with a final question to think about. Maybe the whole goal of great engineering isn't to achieve some kind of flawless, impossible perfection. Maybe the real genius is in the endless, fascinating search for the best possible compromise.